Gnanam Paramam Dheyam. Knowledge is supreme.
Okay, so let us summarize what we have done in last lecture and couple of lectures before that. What we did was K any field, n non-zero natural number, and the assumption n not equal to 0 in K. So that is GCD of n and characteristic of K. These are co-prime. Then we are studying the field extension K zeta n over K, where this zeta n is a primitive nth root of unity, which is a generator of this group mu n k n. Remember our notation for k n is this k zeta n. This is a multiplicative subgroup of k power n, and it is cyclic of order n. And we have proved that this extension is Galois extension, and we wanted to find the Galois group of this extension. And what we proved is what we proved in the last two lectures, Galois group of k zeta n over k from this group to the automorphism group of this cyclic group mu n k power n. This is a cyclic group of order n, and so there is a canonical homomorphism here, namely sigma goes to the sigma restricted to that, because this is a subgroup of this. So I can restrict, and because it is a restriction, this group homomorphism is injective group homomorphism. And in the last lecture we have proved actually that this group homomorphism is bijective when k equal to q. This is a group isomorphism. Therefore, the Galois group of this is the automorphism group of the cyclic group, and automorphism group of cyclic group of order n is, you can identify this cyclic group, this automorphism group with the group Zn cross. And how is the identification gone? That is, if you have an automorphism, it will map generator to a power of generator, and that power should be co-prime to the order of the generator, and therefore it is mapping to that. This is the identification. So for Q we have the complete answer, namely the order of this Galois group is precisely the order of this automorphism group, which is precisely the order of this Zn cross group, which is precisely Euler's torsion function phi n, the value of the Euler's torsion function at n. Now we want to do this for finite field case. So characteristic P case, where K is a prime field of characteristic P. This was a prime field of characteristic 0. Now we are assuming that K is actually I will do little bit more general. Actually I will assume that K is a finite field of order Q, where Q is, and characteristic has to be prime. Characteristic K is P positive. Therefore, this Q, the number of element has to be power of the characteristic. So I will denote Q equal to P power E. And we do the same. What do? We are now N, which is co-prime to P, and we are interested in finding out what happens to this map. This is FQN over FQ. This is Galois group, and this automorphism group, OT mu n, don't write mu n here, mu FQ power round bracket n. So this FQ, this is nothing but the splitting field of the polynomial x power n minus 1. That means we are attaching all the roots of this polynomial to this field, and we are considering the field extension. Now, what we know, we do not know what is the order. We only know that this is a subgroup. This map is injective. This restriction map, this is injective. That is the only information we have. Group homomorphism. And these we know, this is identified with Z mod n cross. So this order we know, this is phi n. And in case of characteristic 0, we actually prove this map is bijective. So then the order of the Galois group in the characteristic 0 case, it is same as phi n. We actually found the minimal polynomial. Now here also we know that this is a Galois extension. Therefore, order of this group I know. Order of this group is precisely degree of the minimal polynomial of zeta n over FQ. Minimal polynomial of this, because this is because this extension is generated over FQ by the root, primitive root. That we know, we know that information because this is a splitting field and zeta is a generator of this group mu of FQN. This is cyclic. So if I know one element there, we know all the elements there with our powers of sigma. Therefore, this extension is cyclic. Therefore, we know this is Galois extension, and the order of the Galois group equal to the degree of the field extension, which is in this case, because it is simple, it is degree of the minimal polynomial. This is all we know. Now we want to check, it is not bijective in general. So we want to check therefore what is the image, and the extra information we have in a finite field case is that this group is cyclic. We know. Now we will use the information, the fact that I will write on the next page. This group Gal FQ zeta n or FQ is cyclic with generator. I know also generator, not only I know it's cyclic, I know also generator. What is the generator? It is the Frobenius FQ. That is, this is the map from FQ zeta n to FQ zeta n. It maps any element y to y power q. So, this, remember that this FQ zeta n is also finite field, and it will have some number of elements. How many elements? Let us write that also. FQM, this is a finite field with m elements, and what is m? M should be the degree of the dimension of FQ round bracket n over FQ. The dimension, this is the degree, that is m. And we know this Galois group therefore has cyclic of order m. So this FQ has order of FQ is m, which is also the order of the Galois group. Right, and now I want to see I want to write down now the identification more precisely, because we want to see what is the image, and because the map is injective, the image of a cyclic group will also be cyclic. The image will be generated by the image of a generator. Therefore, I know. So therefore, we have to understand the identification. So here, so I will write it once more. So this is Gal FQN over FQ. This the injective map is given to the automorphism group of mu FQN. These are the roots of unity in FQN, and this map is sigma going to sigma restricted to that, because this is mu FQN. These are the roots of unity inside FQN. They are all of them there. This is a group of order, cyclic group of order n, and zeta n is a generator. This is what all know, and then we know FQN round bracket n, this is nothing but FQ zeta n. This all we know, and then we have identified this identification with Gn cross. And what is the identification? If you have an automorphism tau of the cyclic group, so let me just write down the elements of this automorphism group down here, or I will write it here. Tau, if it is an automorphism of this group, mu n FQN to mu n FQN, so the automorphism of a cyclic group will map a generator, the zeta n, to a generator, but I know all the generators of the cyclic group. If I know one of them, if I know the order of the group, then I know all the generators. All the generators will be of the form zeta n power r, where r is coprime to n. GCD of r and n equal to 1. And then we are identifying this tau. This tau is uniquely determined by the r. So I could have simply written this tau as tau r. So each coprime integer r to n will give you tau r, and each tau will give you r. So the identification of this with this is r. This is r. That is the identification. And this r, we are reading mod n. So this, strictly speaking, it is r. I should write r Rn when we are reading r modulo n, and that is clearly an element here, because r and n are coprime, so they are precisely the units in this ring. So therefore, our problem is where will Frobenius, which is a generator of this group, where will it go under this identification? That is what we want to understand. Alright, so where will Frobenius go? So I will, okay, I still have the space here, so I will use now the green color. So we are interested in where will Frobenius go. What is the Frobenius? Frobenius is denoted by that FQ. And FQ, what is the FQ map? That maps any element y of the field to y power q. So, and where will it go here? That is Frobenius restricted to this group. That means restricted to the unity, the roots of unity. But where will that map zeta n? That zeta n will get mapped to zeta n power q. And q, what was q? Q was p, that power of p. The q was a power of the characteristic. So q was p power e. And that one I want, so where that q goes to, you are reading that q, where will this Frobenius will go then? This q reading mod n, and then that is reading mod n is this notation. So q goes to this. So therefore, the image of this Galois group in this generated by that q. So I will write here the image of the Galois group, gal fq power n over fq, is in Z mod n cross is generated by Qn. That integer q, which is the power of p, will generate the image of the Galois group. So in particular it is cyclic. So therefore we have to find, if I want to find the order of the Galois group, I have to find the order of the generator. So therefore, to determine the order, the cardinality of the Galois group, we need to determine the order of fq. And hence to determine the order of its image, which is the residue class of Q, in the group Z mod n cross. And this order I am going to denote by order of Q n. Suffix n, this is precisely the order of the residue class of Q mod n in the group Zn cross. This is what we need to compute. In other words, what we proved is the Galois group, the order of the Galois group this order equal to order of Qn. This is by definition order of the residue class Q in Zn cross. So this is what we proved. So let me write this as a theorem. I will summarize in the theorem. And so theorem, what we proved is the following. So we are taking p prime number and q is the power of p, the exponent, and we are considering the polynomial and n integer, n non-zero natural number, n is co-prime to p, and we are taking the fqn. This is the splitting field of the polynomial x power n minus 1 over fq, and we are denoting qn. This is the residue class of q in Z mod n, and note that this q and n are co-prime because q is the power of p and p doesn't divide n, so this is an element here. Okay, with this notation, then we know that the degree of the field extension this is equal to the order of the Galois group and we know it is a Galois extension, therefore this equality. In fact we also know that this group is cyclic, so we have used that information to check that this order is nothing but order of qn. This is precisely by definition order of qn in this group. And what is the order then? But q is the power of p, and I know what is the power of this is precisely the order of order n p power e, and I know how do you compute order of a element, order of an power of an element in terms of the element. So this order is same thing as order of p divided by GCD of m and e. And what is m? M, where m is m equal to this order. Whatever it is. So we have to. So this I wrote the last two equalities I wrote precisely for the calculation purpose. So order of p power e. So you only have to calculate order of that prime number p in Z, that mod n, and we have to go mod divided by the GCD of m and e. So where m is the order of that group where we are working. So this order of m is also equal to order of, this is the order of m in this group. So this m is the degree of this field extension. So that is the complete answer to this. And now therefore what will be it is therefore question remains, what is the minimal polynomial? Whatever it is. So I know therefore the phi n. So I will just write a statement over fq. The cyclotomic polynomial. What is the cyclotomic polynomial? You take a phi of n, that means you take all elements of order n, x minus zeta, and order of zeta is n. This is a cyclotomic polynomial. This order, this polynomial now split into how many factors? I know this group has order. This group has order so much, and this is a subgroup of this group Z mod n cross. So therefore, the cyclotomic polynomial splits into how many irreducible factors? The total was phi n, the degree of this polynomial is phi n, and among them I have to calculate, I have to take order NQ divided by order NQ, because that is the order of this subgroup. That is the order of that subgroup. So cyclotomic polynomial will split into so many prime factors of degree order Qn. Because each irreducible factor will give you finite field extension of the same degree. And therefore, this polynomial will split into so many linear factors, so many, not linear, so many prime factors, and each will be of this order. So phi n will be equal to pi 1 to pi r. They have no multiplicities, because there is no repeated zeros here, because of our assumption n is not divisible by p, and so each one of them will have degree this. So with the degree of pi I equal to order Qn. So that is the complete information about the Galois group of a finite field. What we have proved is the following. In particular, G FQ power round bracket n over FQ, this is a cyclic group of order which divides order of P mod n. See, because an answer should be in terms of the given data, and given data is we have an integer and we have P. Because once we have P, we have Q. So this answer depends only on P and N. Okay. So the divisor of this. Okay. So the particular case is what? So in particular, let us look at the case when order of P is 1. What does that mean? This means what? If order of P is 1, that means what? That is P mod n is order 1. That means P has to be congruent to 1 mod n. Order 1 in which group? We are looking at this group, Z mod n cross. And order 1 element here is precisely the identity element, and identity element is precisely 1. So that means 1 and P coincide in this group, that is P is congruent to 1 mod n. So in this case, therefore, the order of the Galois group, which is the divisor of this order, but this order itself is 1. So there the Galois group has order 1. That means these fields are equal. So then Gal FQ and FP, not P, P, FP n over FP. This has to be trivial. In particular, therefore, FQn, FPn equal to FP. And when can this occur? When will this occur? That will mean that the phi, the cyclotomic polynomial should have 0 in P only. That is if and only if. So which is if and only if phi n has a 0 in Fp. So that is if and only if phi n at A is congruent to 0 modulo P for some A in integer. It's clear? So, here you see this equality means this was a splitting field of x power n minus 1, and this is generated by the roots of the order 1 order n elements of that multiplicative group consisting of roots of unity, that is all contained in Fp. In particular, this phi n has a 0, but phi n has a 0 means in Fp, that means at some A it is 0, but mod P everything. So, that means this. So, with this I will deduce further more corollaries from this in the next lecture, and then I will switch on to more examples of field extensions which are Galois, and debating how do you realize any finite abelian group as a Galois group over Q. Okay. Thank you.